Hey everyone, your favorite astronomy education guy is back. And for those of you who are new and did not see me last year, don't worry, I'll be your favorite very soon. So I'm Danny Barringer. I'm a graduate student at Penn State in the Department of Curriculum and Instruction now. I've had a bit of a weird path through grad school. You can totally talk to me about that later. And I'm going to be telling you about some of the work I've been doing. I started doing it with Chris Palma, but this past semester, Rick Duschel has gotten involved as well with the really in-depth part of the development of this coherent content storyline on exoplanets that I'm going to tell you about. But first, I'm going to give you a bit of a summary of what I talked about last year because this is all relevant. So I'm developing a course for Penn State called Astro 850. Which is a course that is designed for pre-service high school teachers on exoplanets. And it's going to be an elective course they can take as part of the MED in Earth Science program online. And Astro 850 is designed to use activities designed around this claims evidence reasoning framework that Sunny very briefly outlined for you, and to engage students in authentic science practice. I'll tell you a bit more about that later because it becomes particularly relevant when we start talking about NGSS, the Next Generation Science Standards. So for this talk, I'm going to start by telling you what is a coherent content storyline in more detail and why does it matter. Then move on to the Next Generation Science Standards. Because this is a course that is being built for high school teachers, it's incredibly important that we're including and taking into account the standards that high school students are going to be held to. And then I'll talk a little bit about running these activity-based courses in an online setting. I had a little bit of practice doing this with the introductory lab class that I ran this past semester. It was an in-person class admittedly, but for some of the activities, I admittedly used them as guinea pigs. I mean, what was worse that was going to happen? It's my last semester TAing. Are they going to give me bad teaching reviews or something? No, they actually seem to enjoy them. So, why use a coherent content storyline, and what really is it? So the idea of a coherent content storyline goes back to a 2006 study which looked at a particular data set called the Trends in International Mathematics and Science Study, TIMSS, comparing the education or the instruction basically across a number of countries. The video evidence showed that the United States, compared to other high-performing countries, while there were a lot of activity-based lessons, the activities themselves lacked a strong connection to those lessons. They were kind of a bunch of activities mashed together without some driving force behind them, some larger organization. This leads to another problem that was also observed with the United States, where you get this mile-wide, inch-deep problem of trying to cover a lot of material, but only covering it at a very surface level. So coherent content storyline is specifically a way to plan and organize a course. Yes, for those of you who were here last year, I did use this slide already. But it's a great one, so I'm going to use it again. For a coherent content storyline, you want to start with what is the big idea that I'm trying to get across. And this is going to be some kind of a phenomenon or a causal model, something like that. Once you know what you want to get across to them, develop what's called the upper anchor statement. This is the statement of the learning goals for this class. Basically, what do I want the students to know coming out of my class? From there, of course, you can delve into, OK, to understand these, what are the course topics going to be? And then around those, plan out the lessons and activities. This ensures that these lessons and activities are all going to be related back to this big idea. More importantly, perhaps, is the way that they build on one another. This is the example of the storyline that I have been working on. Starting with the basic question of, how do we know that exoplanets are common in the universe, in our galaxy, and so forth? It all starts with our solar system, of course. We look at patterns in the solar system, things like We have terrestrial planets that are close to the sun, gas and ice giants that are far away. Everything orbits in the same plane. Everything is orbiting in pretty much the same direction and rotating in mostly the same direction with like 2 odd cases there. So it tells us that we formed out of, you guessed it, based on all the previous talks, a disk. And then what we will need to look at is, okay, we see these processes occurring in our solar system, or we see the evidence for them. Now you look elsewhere and see, okay, it looks like these processes really are occurring in other star-forming systems as well. Cool. So we kind of expect exoplanets to be everywhere, but we got to figure out how to find them. Once we figure out how to find them, we find them, and holy crud, there are a lot of them. So, and there are a lot of very strange ones, so we go into a bit beyond just planets are common. How did the planets get to the way they are? So we talk about the interactions that occur between the bodies in planetary systems, because this leads to some really cool stuff, and it's actually very relevant for our solar system as well. And of course, we want to talk about the thing that everybody wants to know about exoplanets. Is there life on these planets, potentially, and how would we look for that? But first, I'm going to give you a just brief overview about what the next generation science standards are all about. Traditionally, science standards have just focused on these content areas, the disciplinary core ideas. This is the content knowledge stuff, what you normally think of for standards. What do the students have to know, more or less like factually? And it's separated into 3 main areas: life sciences, physical sciences, earth sciences. OK, cool. The next 2, the science and engineering practices and the cross-cutting concepts, are the parts that are completely new for next generation science standards. We want to get the students an idea of how science is done. And so some examples of these, there are actually 8 science and engineering practices that are listed in the full document, but these are just some examples. And the cross-cutting concepts, then, are not disciplinary core ideas. These are not your typical, students should know that like the Earth goes around the sun. These are kind of threads and recurring themes that connect your disciplinary core ideas across the various levels. Things like ideas about energy and matter and stability, change, and patterns and things like that. So now that you're all experts on the next generation science standards, how do exoplanets fit into NGSS? Well, unfortunately, not strictly speaking. Because, of course, exoplanets are an incredibly new field that really haven't made their way into curricula below like introductory level astronomy at the college level. So why should teachers care about that? Main thing to note is that standards are not necessarily a list of the ways in which you should teach your students something. Instead, using exoplanets to talk about these, in this case, the disciplinary core ideas that I've listed here, provides another context for looking at them entirely and connects them in completely different ways than you would see just by following, the letter of what is in the standards. Secondly, referring to the cross-cutting concepts, the 2 that I focused on the most in developing the curriculum for Astro 850 were patterns and ideas of stability and change. Patterns are incredibly important to our detection of exoplanets because, as you can see in like this sample light curve, you're looking for a pattern, a recurring decrease in the brightness of a star that indicates that there is a planet transiting in front of it. Of course, there's a little bit more work to figure out that's actually a planet and all, but I'll leave that up to the people with the really fancy radio velocity instruments. And stability and change. So while our solar system now is very stable and everything is pretty much set in its orbit, it wasn't always the case. The NEAS model, which is illustrated here, basically demonstrates that about, what was it? A few hundreds of millions of years into the formation of the solar system, things went completely haywire. Uranus went from being the 8th planet orbiting the sun to the 7th and kicked out a whole bunch of comets and things like that, essentially planetary leftovers, that eventually went on to form the Oort cloud. And this also changed where the orbits of the planets were. It could have completely different consequences in terms of the shapes of the orbits, but in our case, most of the orbits actually turned out to be fairly circular. And the claims evidence reasoning framework, the way that we are developing all the activities, or really I am, admittedly, developing the activities for this course, is a way that students can engage with actual data or observations. The example I'm showing here is this little web game called Super Planet Crash. If you haven't heard of it, check it out. It's addictively fun. But what I have the students do here is you have planets orbiting this star. You can adjust the mass of the inserted planet, and you get a higher score when you use more massive objects. But throwing a lot of massive objects into a 2AU distance from a star obviously makes things go a little unstable. So the goal here for this game is to try to create a stable system. And what I have the students do is play around with this and look at what are the conditions that you're developing or you're observing for stability in these systems, and why is that going to be the case? Now on to the very last part, the dealing with these kinds of activities in an online setting. Traditionally, students will write up claims, evidence, and reasoning in a group and present that to the class. Generally, they'll write it on a whiteboard. The term that's used in a lot of papers is the board meeting. But they write up on a whiteboard, and they talk about, this is what we observed, this is what we found, and they get critique on it from other students. This is scientific argumentation in practice. Moving the discussions online, of course, changes a lot of this because you don't have the face-to-face interactions, and you have to switch to a more written style of critique, argumentation, than you would have in a normal face-to-face class, which is usually where claims, evidence, reasoning type activities are used. One interesting thing that this does, though, is, as I noticed, it gives you a window into the thinking of the students that are making the arguments, both in terms of presenting what they determined and students who are maybe arguing against the way that they grouped, the gas and ice giants separately. The last thing, of course, is deadlines. Because this is not face-to-face, you need to make sure that students have, provide feedback on your other students' work by this time. Because then the students need to be able to respond to the critiques of their work. So, I'll leave my summary slide up here, and I will take questions at this time. Thank you.
So Dana, you mentioned that exoplanets don't fit into the NGSS system.
Strictly speaking.
Strictly speaking. And so are you envisioning that instructors will go out of their way to sort of convolute the system so that they can talk about exoplanets in particular, or are you using it as sort of where in the curriculum do you see exoplanets fitting?
I see it as a way to grab students' attention, frankly. Let's face it, exoplanets are really cool. They're one of the most interesting fields right now because it's growing incredibly fast, and planets, unlike a whole lot of the other stuff in astronomy, is something that we can relate to very directly, being on a planet ourselves. So thinking about that, well, there are other planets out there, what about other planets with life out there, is just one of the most fundamental questions of our existence. And you can bring that into a classroom context just on the fact that students can find it more interesting than maybe, rehashing the same things about Earth. But they give you opportunities on all of those same disciplinary core ideas you would be hitting otherwise, just doing it with a slightly different planet or planets in mind.
One in the back, Bradley.
All right, so piggybacking on that question, so are you envisioning this as a semester kind of course, or is it going to be something that you would, plug into certain classes, like patterns, you put it into a physics class and a chapter, and you give a case study almost?
Okay, so Asteroid 50 itself is on a course on its own, but the idea of the activities is that they can kind of slot into a course individually. These are things that really we want teachers to be able to take into their own classrooms, which is why it's so important that they're NGSS aligned and things like that. Ideally, it would be kind of a curriculum unit that you do all together, in sequence, so you're not breaking up this coherent content storyline that I've put together. But really, if you just want to, take out a particular part of this and use it, by all means, that's totally fine with me.
So this coherent content storyline, can this be scaled down to a single lecture for someone who's like a TA for a larger course who needs to stay on a stricter schedule? Could they incorporate some of these ideas to, enhance their own lectures?
I'm not going to say no to that. So the main thing to take away from that, if you're scaling it down to, a single class's worth of material, is to come up with what do you want students to get out of this particular, lecture activity or lecture plus activity, whatever it happens to be, and make sure that you're playing around that with that in mind throughout the entire process. Spell out what those connections are. It's not like your learning goal is some thing that the students never get to see. Ideally, they should know exactly what they're working towards the entire time. That's what you start with, actually. Day one of a class for Asteroid 50, students will be introduced to the Kepler orrery because it shows a lot of planets and the diversity of the systems that Kepler has found. Of course, it's not complete because we found planets other ways, but they'll get all of these as caveats as well. But scaling it down, I'd say works on that level. Just make sure that things are consistent and coherent to whatever your main goal is.
Let's go ahead and thank Danny again.